9.6 Valence bond theory. Overall, hybrid orbitals provide a convenient model for using valence bond theory to describe covalent bonds in molecules in which the molecular geometry conforms to the electron domain geometry predicted by the VSEPR model. The picture of hybrid orbitals has limited predictive value. When we know the electron domain geometry, however, we can employ hybridization to describe the atomic orbitals used by the central atom in bonding. So as an overall summary, the first thing you should be doing is drawing a Lewis structure for the molecule or ion, and then using the VSEPR model to determine the electron domain geometry around the central atom. Then you will specify the hybrid orbitals needed to accommodate the electron pairs based on their geometric arrangement, and you can refer to table 9.4 in your textbook for that. So we're going to talk about different ways that we can have overlapping. And the first type is called a sigma bond. In the covalent bonds that we've considered thus far, the electron density is concentrated along the line connecting the nuclei, which we call the internuclear axis. In other words, the line joining the two nuclei passes through the middle of the overlap region. So here we see two hydrogens approaching each other, and again, that overlap region is called the sigma bond. It's a head-to-head overlap, and it has cylindrical symmetry of electron density about the internuclear axis. We can see the same thing in the other two examples on this page with the 3p overlap in Cl2 or the 1s and 3p overlap in HCl. Pi bonds are characterized by side-to-side overlap, electron density above and below the internuclear axis. To describe multiple bonding, we will consider pi bonding. This is one result of overlap between two p orbitals that are oriented perpendicular to the internuclear axis. Unlike in a sigma bond, in a pi bond the electron density is not concentrated on the internuclear axis. The sideways orientation of the p orbitals in a pi bond makes for a weaker overlap. As a result, pi bonds are generally weaker than sigma bonds. In almost all cases, single bonds are sigma bonds. A double bond consists of one sigma bond and one pi bond, and a triple bond consists of one sigma bond and two pi bonds. Sample exercise 9.5, hybridization. Indicate the hybridization of orbitals employed by the central atom in NH2- and SF4. We're given two chemical formulas, one for a polyatomic anion and one for a molecular compound, and asked to describe the type of hybrid orbitals surrounding the central atom in each case. To determine the hybrid orbitals used by an atom in bonding, we must know the electron domain geometry around the atom. Thus, we first draw the Lewis structure to determine the number of electron domains. The hybridization conforms to the number and geometry of electron domains around the central atom, as predicted by the VSEPR model. So in the Lewis structure of NH2-, we see that our electron domain geometry is tetrahedral. The hybridization that gives a tetrahedral electron domain geometry is sp3. Two of the sp3 hybrid orbitals contain non-bonding pairs of electrons. The other two are used to make the bonds with the hydrogen atoms. The Lewis structure and electron domain geometry of SF4 have been shown in exercise 9.2. The sulfur atom has 5 electron domains around it, giving rise to a trigonal bipyramidal electron domain geometry with an expanded octet of 10 electrons. A d orbital on the sulfur must be used. The trigonal bipyramidal electron domain geometry corresponds to an sp3d hybridization. One of the hybrid orbitals that points in an equatorial direction contains a non-bonding pair of electrons. The other 4 are used to form the SF bonds. Practice exercise. Predict the electron domain geometry and the hybridization of the central atom in these two samples. Again, single bonds are always sigma bonds because sigma bonds overlap is greater. This results in a stronger bond and more energy lowering. Multiple bonds. In multiple bonds, one of the bonds is a sigma bond and the rest are pi bonds. So in a double bond, you have 1 sigma and 1 pi, and in a triple bond, you have 1 sigma and 2 pi bonds. In a molecule like formaldehyde, an sp2 orbital on carbon overlaps in sigma fashion with the corresponding orbital on the oxygen atom. The unhybridized p orbitals overlap in pi fashion. In triple bonds, as in acetylene, two sp orbitals form a sigma bond between the carbons, and two pairs of p orbitals overlap in pi fashion to form the two pi bonds. Sample exercise 9.6, describing sigma and pi bonds in a molecule. We're going to examine formaldehyde and describe how the bonds in formaldehyde are formed in terms of overlaps of appropriate hybridized and unhybridized orbitals. The carbon atom has 3 electron domains around it, which suggest a trigonal planar geometry with bond angles of around 120 degrees. This geometry implies sp2 hybrid orbitals on the carbon. These orbitals are used to make the 2 carbon-hydrogen and 1 carbon-oxygen sigma bonds to carbon. There remains an unhybridized 2p orbital on carbon, perpendicular to the plane of the 3 sp2 hybrids. The oxygen atom also has 3 electron domains around it, and so we will assume that it has sp2 hybridization as well. One of these hybrids participates in the carbon-oxygen sigma bond, while the other 2 hybrids hold the 2 non-bonding electron pairs of the oxygen atom. Like the carbon atom, therefore, the oxygen atom has an unhybridized 2p orbital that's perpendicular to the plane of the molecule. The unhybridized 2p orbitals on the carbon and the oxygen atoms overlap to form a carbon-oxygen pi bond, as illustrated. Practice exercise. Consider the acetonitrile molecule, predict the bond angles around each carbon atom, describe the hybridization at each of the carbon atoms, and determine the total number of bonds in the molecule. Delocalized electrons. We're going to talk about resonance again. When writing Lewis structures for species like the nitrate ion, we draw resonance structures to more accurately reflect the structure of the molecule or ion. In reality, each of the 4 atoms in the nitrate ion has a p orbital. The p orbitals on all 3 oxygens overlap with the p orbital on the central nitrogen. This means the pi electrons are not localized between the nitrogen and one of the oxygens, but rather are delocalized throughout the ion. Another example, the organic molecule benzene has 6 sigma bonds and a p orbital on each carbon atom. In reality, the pi electrons in benzene are not localized, but they are delocalized. The even distribution of the pi electrons in benzene makes this molecule unusually stable. Sample exercise 9.7, delocalized bonds. Describe the bonding in the nitrate ion. Does this ion have delocalized pi bonds? Well, we just discussed this. In each of these structures, the electron domain geometry at nitrogen is trigonal planar, which implies sp2 hybridization of the nitrogen atom. The sp2 hybrid orbitals are used to construct the 3 NO sigma bonds that are present in each of the resonance structures. The unhybridized 2p orbital on the nitrogen atom can be used to make pi bonds. For any one of the 3 resonance structures shown, we might imagine a single localized nitrogen-oxygen pi bond formed by the overlap of the unhybridized p orbital on nitrogen and a 2p orbital on one of the oxygen atoms. Because each resonance structure contributes equally to the observed structure, we represent the pi bonding as spread out or delocalized over the 3 bonds. Practice exercise. Which of the following molecules or ions will exhibit delocalized bonding?